Okay, so this is like a solution for exam 2. So the first question says a ball is launched from 2 meters off the ground at 30 degrees above horizontal with an initial speed of 15 meters per second. And so it would follow a parabolic path. Something like that. And you're just asked to find the highest point that it reaches, the greatest height. I'm going to use a coordinate system that's on the ground below where it's launched from. That starting height is 2 meters. And so t equals 0 is going to be the instant that it's launched. Time final is going to be when it reaches the highest point. We don't know how long it takes to get to the highest point, so we don't know TF. We know that during this whole flight, the acceleration is 0, negative 9.81. The initial position is 0, 2. The final position, we're trying to find the y component. The initial velocity is the initial speed of 15 meters per second times the cosine and sine of 30 degrees. And so that is 12.99 for the x component and 7.5 for the y component. And then any question that asks you about the highest point of an object's flight, at that point, you know that the y component of velocity is equal to 0. So our v f y is equal to 0. Okay. So the equation that works with all this is 2 ay times the quantity pfy minus piy is equal to vfy squared minus viy squared. So negative 19.62 times the quantity pfy minus 2 is equal to 0 squared minus 7.5 squared. And so divide both sides by negative 19.62. Notice this negative doesn't get squared. Okay, so you get PFY is equal to positive 4.87. Then the second question, you have these two carts. The one on the left has a mass of 15 kilograms. The one on the right has a mass of 25 kilograms. There's a 40 Newton force there and a 90 Newton force there. And we want to calculate first the acceleration vector of the two carts. Second, we want to calculate the force vector on the 15 by the 25. And then third, we want the force vector on the 25 by the 15. This is a case where both of these objects have the same acceleration, and you know that because there are no pulleys in this problem. And so you're going to start by isolating the whole system together. The total mass is 40. So the weight is 40 times 9.81, so 392.4. And then we have an upward force on the wheels of N total, and then the 40 and the 90. So Newton's second law says 40, 0, plus 0, negative 392.4, plus 0, N total, plus negative 90, 0, is equal to the total mass, 40, times the acceleration. This is moving along the x direction, so our acceleration is just going to be a0. Everything we're looking for is given in the x components. So I'm just going to use the x equation here. And that says 40 minus 90 is equal to 40a. So negative 50 is equal to 40a. Divide both sides by 40, and you get that a is equal to negative 1.25 meters per second squared. The total acceleration we represented as a is equal to a for x, 0 for y. And so plug in our value of a, this variable value, into that vector, and you get that the acceleration vector is negative 1.250. So that's all for part A. And now for parts B and C, we have to isolate individual ones of these. I guess I'll start by isolating the 15 kilogram. You could actually do this problem by isolating either one of them, if you remember Newton's third law. So the 15 kilogram cart has the 40 Newton force acting over here, the weight of 147.15, the pushing force from the ground that I'll call N15, and then the only other place that there's contact with the surroundings is where the 25 is pushing on the boundary. And so I'll call that force R, and that's the complete free body diagram. And Newton's second law says 40, 0, plus 0, negative 147.15, plus 0, N15, plus negative R, 0. is equal to the mass, 15, times the acceleration vector that we just figured out, negative 1.250. And the x equation here says 40 minus r is equal to 15 times negative 1.25. And so r is equal to 58.75. Well, what we really want is this force. This is the force on the 15 by the 25. And so now we have to plug that r vector, that r variable value into this vector. And so the force on the 15 by the 25 is negative 58.750. And then you can isolate the other body and go through that all again. You'll get the right answer. But an easier way to do it is recognize that this is a Newton's third law pair. This is just two objects applying forces to each other. And so the force on the 25 by the 15 is the negative of the force on the 15 by the 25. And so that's positive 58.750. The force on the 15 by the 25 is this way at 58.75. And the on the 25 by the 15 is, it's a little crooked, this way with the same magnitude. That's what Newton's third law says has to be true. Any questions about that one? Then number 3 was a friction problem. We have a ramp at an angle of 25 degrees. And a 10 kilogram mass is sliding up the ramp. So this arrow is just showing the direction of motion. That's not a force, that's just a direction. And for any of these rolling or sliding problems on inclines, the coordinate system is going to have the y-axis pointing straight out. And so the x-axis in this case has to point like that. And the one force vector that's going to be complicated is the weight force now, because that's not at the same angle as any one of these coordinate axes. So I'm going to start by calculating this weight force. Okay, so this weight force has a magnitude of 98.1. I haven't even drawn the free body diagram yet, but I'll do that next. And so to get from the x-axis to the weight force, that angle is 295 degrees. Okay, so the weight force is going to be 98.1 times the cosine and sine of 295. So here's a free body diagram. So this weight force is 98.1. There's a pushing force from the surface. I'll call that N. And then the friction force is opposite the direction of motion. So in this case, it's this way. And the magnitude is the coefficient of 0.3 times that normal force N. And so Newton's second law says, so the weight force is 98.1 times the cosine of 295 degrees, 98.1 times the sine of 295 degrees. And then the normal is 0n. The friction is in the positive x direction, and that's 0.3 times n. And this is equal to the mass times the acceleration. This is going to move along the x-axis. The y-axis, the y equation says y. Okay, so the y equation says negative 88.91 plus n is equal to 0. So you can solve that for n. And then plug that into the x equation. And you get 41.46 plus 0.3 times 88.91 is equal to 10a. Bless you. And so A is equal to positive 6.81. The acceleration vector is a0. Just plug this value in for a, and you get an acceleration vector of 6.810. Or in other words, 6.81 meters per second squared down the ramp. Okay, so that's part A, and that's most of this question. And then it asks you, is this speeding up or slowing down? All you have left for part B is to figure out if the acceleration is in the same or the opposite direction from the velocity. The velocity was up the ramp. The acceleration we just figured out is down the ramp. And so this is slowing down. Any questions about that one? And then the last one we have a rolling cart here that has a mass of 3 kilograms. and it's connected to a hanging mass of 2 kilograms. And we want to figure out the acceleration vector of the 2 kilogram cart and the tension in the cable. So in this one, the accelerations of those two objects are not going to be the same. You know that because there's a pulley in this problem. And so we are going to start out by choosing one of these to isolate instead of isolating the whole thing at once. I guess I'll choose the 3, but it doesn't matter which one you choose first. The weight force is 29.43. There's a pushing force up of N. And then there's a pulling force from the cable. I'll call that T. And so Newton's second law says 0, negative 29.43 plus 0n plus T0 is equal to 3 times the acceleration. This thing is free to move along the x-axis, so I'm going to write this as A0. And the x equation says T is equal to 3a. All of this stuff we're trying to calculate is related to T and A, so I know that we don't care for this one about the y equation, so I'm just going to stop there and move on to the next body. So now the free body diagram of the 2 kilogram object. There's a cable tension up and a weight down. And so Newton's second law says 0, negative 19.62 plus 0t is equal to the mass. And now for the second body, you always have to think about the acceleration for a second. You have to come up with a direction. So we're going to say if the first body moved an inch in its positive direction, that means in the positive x direction in this case, where would the second body go? It would go an inch down. And so I know my acceleration is going to be in the negative y direction, or that's how I'm going to represent it here. Okay, so I'm going to put this as 0, negative a. Then the y equation says negative 19.62 plus t is equal to negative 2a, and that's my second equation. So now those two boxed equations you're going to solve by substitution. For my first boxed equation, I know that t is equal to 3a. So I'm going to substitute 3a in place of t in the second one. So negative 19.62 plus 3a is equal to negative 2a. And so 5a is equal to 19.62. And so A is equal to 3.92. Well, we want the acceleration of the hanging mass. And we know that the acceleration vector of the hanging mass, we represented that as 0, negative a. So just plug A in, 3.92 in for the a in the vector. And we get that the acceleration of the 2 kilogram object is 0, negative 3.92. And the last thing we're looking for is the tension. So for part B, you can use any one of these equations you want that'll let you calculate T now that we have A. The easiest one, I suppose, would be this one. So the tension is just going to be 3 times what we got for A. So T is equal to 3 times 3.92. So T is equal to 11.77 about. Any questions about that one? Okay, you know, there were plenty of good scores, but there were also a lot of scores that I think were lower than people want. You might want to look at this test and go back and see, look at the relationship between these test questions and the daily assignment problems. If you know the steps to do all of those daily assignment problems going into the exam, then you're going to do well on the exam, okay? There's nothing on here that doesn't follow steps from those daily problems. And so remember, I'm happy to help in office hours or whatever, but the main thing you have to do is make sure that going into the test, you remember all the steps for those daily problems, okay? All right. Well, last class, we started talking about conservation laws. And the first conservation law, the simpler of the two, is conservation of linear momentum. And so we're done talking about that. Does anybody have any questions? Want me to go over any of the homework questions on conservation of linear momentum? Okay, so now we're going on to conservation of mechanical energy. And this one definitely is a little more complicated. There's a few more things that you have to kind of wrap your head around to make sense out of this. I mentioned before that one way to identify when to use conservation of linear momentum, conservation of mechanical energy is when a problem is asking you to relate an object's location to its speed. It's not a foolproof thing because there are problems in particle kinematics that also do this. But this is one thing that says, okay, maybe energy is the way to go on this. Okay. And so I'm going to sort of give you the punchline first, and then I'm going to go back and do all the definitions that we need to understand this. But this is where we're going to end up. If the only forces that do work on a body are conservative, then capital U plus capital T is a constant, where capital U is the potential energy, and capital T is the kinetic energy. Okay. So this is conservation of mechanical energy. Here are the things that we haven't talked about yet that we need to define before we can use this. The idea of work. Okay, we need to understand what work is. We need to understand what conservative and non-conservative forces are. And we need to understand what kinetic and potential energy are. Okay, so I have to give you those 4 definitions before we can make sense out of this stuff. But you can see once we make sense out of that, like understanding these things is kind of the biggest part of using this stuff. The equation itself is really simple. Okay, so I'm going to start by defining kinetic energy. Let me say one thing before I go into kinetic energy. I didn't put this in the setup for conservation of mechanical energy, but so conservation of energy always holds. There's always conservation of energy, but energy can express itself in a lot of different ways. There's thermal energy, electrical energy, magnetic energy, all these things. In this class, we're not going to deal with thermal or electrical or magnetic energy or anything. And so the only type of energy that's going to change for our problems is mechanical energy. And that's why we're using this. But if a problem, so if something's temperature is changing a lot, or there's magnetic things going on, or electrical things going on, you also can't use this because we just don't have those terms built into this equation. Okay. Okay, so kinetic energy. Kinetic energy is an amount of energy an object has at an instant. If m is the object's mass, and capital V is the object's speed, then the object's kinetic energy at that instant is 1/2 times the mass times the speed squared. If instead of knowing the object's speed, you know its velocity vector, it turns out it's easy to calculate this from the velocity vector too. So if you know the object's velocity vector, components, you can also calculate the kinetic energy as 1/2 times the mass times the quantity x component squared plus y component squared. Okay, so that's just the relationship between the velocity and the speed, really. The units for all types of energy are the same. And you can express them in a couple of different ways. One way for the energy units to appear is as units of force times units of length. And another way that looks different but actually is the same because of the relationships between these different quantities is units of mass times units of length squared divided by units of time squared. The SI units for energy force times length would be newtons times meters. And equivalent to that is this other one that would be kilograms meters squared per second squared. And since energy is something that's used a lot in physics and other sciences, we give it its own name, the joule. And it's abbreviated with a capital J. Okay, so here are some things to notice about kinetic energy. So first, as an object's speed increases, its kinetic energy increases. The same is true of mass, but for the most part, objects' mass doesn't change, you know. But as the speed increases, its kinetic energy increases. Second, kinetic energy is a number, not a vector. And it's actually always a positive number. So if an object's moving 50 miles per hour, it doesn't matter whether it's going north or southwest. The direction doesn't matter. It has the same amount of kinetic energy. So it doesn't have a direction. And intuitively, you can think of kinetic energy as telling you how much it would hurt if the object hit you, okay? Or how hard it is to stop the object. So the kinetic energy T says how much computer. How much it would hurt if an object hit you. Okay, so let's do an example. Let's say that a car has a mass of 1,000 kilograms and a speed of 30 meters per second. Okay. And let's say that also a turtle has a mass of 0.1 kilograms and a speed of 0.5 meters per second. And we want to calculate which one we would rather get hit by. I mean, you're smart people, so you might be able to figure this out without doing the calculation, but we're just going to be extra careful. Okay, so first the car. The kinetic energy is 1/2 times a mass of 1,000 kilograms times 30 squared. 30 squared is 900. Half of that is 450 times 1,000. So the kinetic energy of the car at this instant is 450,000 joules. And now the turtle, the kinetic energy is 1/2 times a mass of 0.1 times 0.5 squared. So that's 0.25, 0.125, 0.0125. So 0.0125 joules. So I thought it was going to be pretty close, but it wasn't. We'd much rather get hit by the turtle. Anybody have any questions about that? So how could you increase the energy of these things? Well, you probably can't increase their masses much, you know. All you can do is have them go different speeds. If the car was stopped, then the turtle actually would have more kinetic energy than the car, and it would actually hurt a little bit less to just lean up against the car, you know. So the next thing that we have to define is work. And the most important thing to remember about work is kinetic energy is an amount of energy that an object has at an instant. Work is a change in energy. So they're a little bit different in that way. Kinetic energy was an amount of energy at a single instant. The work, capital W, is a change in energy over a time interval that's caused by the application of a force. Okay, so let's think about what we know about kinetic energy. the faster a thing is going, the more kinetic energy it has. Does it make sense that applying a force to an object can change its kinetic energy? It does, because applying forces to things makes them accelerate, and accelerations can make the speed change. They don't have to. They can just make the thing turn, but they can make the speed change. Okay, so if you have an object that's at rest, and then you apply a force to it for a little while, its speed will change, and that'll increase its kinetic energy. So that's what we're talking about here. Okay. So to calculate the work over a time interval, if an object has the displacement vector lowercase d, and a force is applied the whole time, and let's say that force is capital F vector, then the work is equal to the x component of the force times the x component of the displacement plus the y component of the force times the y component of the displacement. That's sort of a funny calculation that we haven't seen before, but it's called a dot product. And you'll see it denoted like this, a vector with a dot and then the second vector. Okay, so let's do a calculation of work for a force that we know. So let's say if a 3 kilogram object goes from a height of 5 meters to a height of 2 meters, what's the work done by gravity? Okay, well, let's think about just physically, like what do we expect to happen here? So the object is going from a higher height to a lower height. Okay, so the object's velocity is downwards towards the ground. So do we expect gravity to contribute to speeding this thing up or contribute to slowing this thing down? Yeah, so we expect it to speed up, and so we expect to get a positive value for work when we do this calculation. Okay, so we expect work to be positive because it's going to be speeding this object up. Okay, so the calculation, we'll say that the displacement vector, let's say that it goes from, well, remember displacement is the ending position minus the earlier position. So the ending position is going to be 0, 2. The starting position is going to be 0, 5. And so that displacement vector is 0, -3. And the units are meters. The force vector that gravity applies is downward with a magnitude of the mass of 3 times 9.81. So this is 0, -29.43 newtons. And now that we have those two things, we can calculate the work. The work is equal to 0, so that's the x component of the force, times the x component of the displacement, which is also 0, plus the y component of the force, times the y component of the displacement. And so we get a work of positive 88.29 Newton meters, or Newton meters are joules, so 88.29 joules. Positive, so it caused an increase in energy. Okay. What do you think would happen to the work if we, so say we still were looking at the effective weight, but this time the object went from a height of 2 meters up to a height of 5 meters? Then you would expect that gravitational force to contribute to slowing that thing down, right? It's acting against the motion. And so you'd expect the work to be negative because it's taking energy away from the body. And that's exactly what would happen. You just have a displacement that's equal to 0, +3. And when you multiplied these together, you'd get a negative work. Okay. Here's a surprising fact to remember based on this definition. If an object doesn't move, forces do 0 work, no matter what the force is. So, like if you push as hard as you can against a wall, you're generating a big contact force. But if you're doing calculations in terms of energy, that contact force isn't doing any work on the wall. Okay. And it's kind of makes sense if you think about it in terms of like, if that force were isolated by itself, would it be speeding the wall up, slowing the wall down? It's not doing anything to the wall. The wall doesn't really notice it, you know. Did you mean like object does not move? Yes, thank you. If the object does not move, then the force does 0 work. Okay, so let me give you sort of the intuitive summary of this. So this is the intuitive result of all this. So first, if the force vector and let's see, how do I want to say this? So if the force vector and the velocity vector, okay, so we were talking about displacement, but now let's think about the velocity as just instantaneously the direction the thing is moving. If the force vector and the velocity vector are within 90 degrees of each other, so if they're kind of roughly in the same direction, this means, okay? Then the work is positive. On the other hand, if the force and the velocity are over 90 degrees apart, then the work is negative. And let me make a note here. Work positive means the force is increasing the object's energy. If they're over 90 degrees apart, then the work is negative, and that means the force is decreasing the object's energy. Well, there's only one case that isn't included in these two. Which one is that? If the force and the velocity vector are exactly perpendicular to each other, you know, exactly 90 degrees apart, then the work is equal to 0. Okay, well, so think of it sort of in terms of parallel and perpendicular parts of acceleration. Think of these forces as causing parallel and perpendicular accelerations. If the force and the velocity vector are roughly in the same direction, then there's an aparallel that's making the object speed up. That's why the energy is increasing. If they're roughly opposite each other, more than 90 degrees apart, then aparallel is in the opposite direction of the velocity, and it's slowing down, so energy is being removed from the system. If they're exactly 90 degrees apart, then that force isn't producing any aparallel at all. It's only producing an aperpendicular, which means it might be making it turn, but it's not having any effect on its speed. Okay, and so that's why then in that case, the energy isn't changing. Okay, let's do an example thinking about this in terms of carts. So imagine this cart moving to the right as a force is applied. Okay, so it's going this way as this force is applied. So first, what would it do to the speed if you applied a force in that direction? In this case, the force vector and the velocity vector are within 90 degrees. And so this cart would be speeding up. Meaning its energy increases. And so therefore, the work is positive. Second, so it's moving to the right. But this time we apply a force this way. Now the force and the velocity vector are over 90 degrees apart. It makes intuitive sense that that force would be slowing that cart down. And okay, so this is slowing down. That means that energy decreases. And that means that work is negative. The change in energy is negative, and work is a change in energy. And then the third case is this thing is moving to the right, and we apply a force to it exactly like this. Okay. Well, if we can apply that force without, it would be sort of tricky to do, but if we could apply that vertical force without also applying a force to one side or the other horizontally, this wouldn't cause any change in speed to this object at all. Therefore, there'd be no energy change. And that means that the work is equal to 0. Okay, so I'm going to give you 3 pretty short problems to do for this class. All of them are just trying to, make you wrap your head around like the directions of forces and what that does to the energy and stuff like that. Anybody have any questions about any of this? Okay, remember there's no lab this week.